Hi, welcome. I want to talk to you right now about some basics about probability, some things that you need to know in order to be able to manage probability and statistics together. We're just going to talk about some basics about how probability works. I expect that you're familiar with probability from prior schooling. So the first thing that I want you to know is that a probability is always a value between 0 and 1. So 0 less than or equal to the probability of some event less than or equal to 1. So I'm actually sneakily introducing a notation here too. We write P of A for the probability of some event. And I'm going to write that as our second, but I want to talk about the first still. So we write P of A for the probability of an event A. So this allows us to refer to the event and talk about its probability at the same time. So A could be anything that happens or anything that might happen. And we write P of A whenever we want to talk about the probability of that happening. So now a probability is always a value between 0 and 1. So this might strike you as surprising if you think about the fact that we also talk about like there's a 50% probability or there's a 10% probability. So those are numbers greater than 1, right? But those are actually just percentages which are shifted 2 decimal places from the actual probability. So a coin flip has an outcome that could be heads, and the probability that the coin flip will be heads is going to be a number between 0 and 1. It's going to be 1/2 or 0.5. And we could refer to that as 50%, but that's this same thing converted to a percentage. So that should remind you of the situation with proportions. Whenever we're talking about proportions, then we have a number between 0 and 1. It could be equal to 0, it could be equal to 1, or it could be somewhere in between. And if we want to express it as a percentage, then we shift the decimal place two places and we get a number between 0 and 100. Because for some reason we like to measure things as coming out of 100 instead of coming out of 1.0. So any 50% probability, any 25% probability is actually a 0.5 probability, actually a 0.25 probability. All probabilities are within this range from 0 to 1. And we have this P of A notation. Now, the probability of an event records the likelihood of an event. And I want you to have some sort of intuition for what those numbers are going to mean, because we're going to be looking at probabilities of events. And I want you to be able to say, oh, okay, it's this number, and therefore that means something to me. So let's talk about some common probabilities and what they might mean to you. So if we say the probability of an event is, so the probability, and I want to just give you an example. So the probability might be 1. That's about as big as a probability can be. That records certainty. So an example of that would be the probability you are watching this video. I'm trying to be cute and use something that that is certain, although in all honesty, you might not be watching this video, you might be listening to this video, so I'm cheating a little bit, but you get the idea. A probability of 0.5 would be, well, literally a toss-up. We call that a toss-up because that's the probability of a coin flip. So for an example of that might be the probability of heads if you're doing a coin flip. So that's a 50-50 probability. You really don't know. It could go one way, it could go the other way. There's no indication one way or another which way it's probably going to be going. I'm going to go all the way down to 0.05. That's a 1 in 20 probability. And that's going to be rare, but not really unusual. So that's rare, but certainly not striking, certainly not like terribly unusual. This is an important probability for us because we will use this probability as a threshold of significance when we're talking about levels of significance. That will be a common threshold of scientific significance. And so this will come up. This will be a very important probability for us to consider. I want you to understand that it records an event which is unusual, but not really terribly striking, 1 in 20. This is, if you've ever played a game called Dungeons and Dragons, this is the probability of a critical hit because it's the probability 1 in 20. So it's the probability of a 20 on a d20. This is a silly game that involves, well, it's a fairly awesome game to be true, to tell you the truth, which involves a 20-sided die. The die itself is very complicated. It has 20 sides, and you roll it, and if it lands, the sides are numbered 1 through 20, and if it lands on the 20, then something good happens. And the probability of that, of course, is 1 in 20, which converted to decimal is 0.05, and thought of as a percentage is 5%. So all of those things are the same. 1 in 20, critical hit. This is sort of rare, but not really very striking, not really unusual. It's nothing to write home about, but it's something unusual. It might make you raise your eyebrow. A key probability that's kind of affecting us right now, I wanted to calculate it for you, 0.0006. This is quite rare, but not really, but not, but you know, very possible, I think. Well, let me simply say possible. This is important probability right now because this is probability of dying of COVID-19. And this is among Americans. And this is true contextually today. For me, today is September 25th. That is the probability if you were to pick a random American alive at the beginning of 2020, the probability that that would have been one of the 200,000 or so people who have died from this disease during this year so far. So far. So that's a much smaller probability than this, but a much larger probability that things that we would regard as generally impossible. Speaking of things that we generally regard as impossible, I want to, or at least we treat as impossible, at least we don't account for. So I've got 5 zeros here and a 2. This is roughly the probability of getting hit by lightning. That is throughout the entire year. That's the probability that you'll be hit by lightning in an entire year. Very, very low probability. And because it's a low probability, we don't plan for it and we don't account for it. At least most of us don't really take this into account as a possibility. We discount this thing as a circumstance that even might happen. I want to throw one more here, 0.000000003. And let me check my notes to make sure that I've got that right because I don't have it memorized. Yep, that's right. And that's the probability of winning with a Powerball ticket. So Powerball is a gambling game, and I want you to take note of the relationship between the probability of getting hit by lightning and the probability of winning with a Powerball ticket. This one of the ways in which people are convinced to participate in these kinds of lottery games and lose their money at them is that these probabilities of winning them are so outrageously small that people really lack the kind of intuition to understand how outrageously small they are. And so we tend to sort of mentally approximate them at larger numbers. This is far less probable than many events we would colloquially call impossible. But it is not, of course, impossible. And then finally, maybe at the bottom of this list, but let me not write on the paint of the wall, we could have the probability of 0 itself. It is certainly sensible to say that the probability of an event is 0. And what we mean when we say that is that that event is literally impossible. This is the probability, for example, that 1 + 1 is equal to 3. That's a literal impossibility. It cannot happen. And therefore, we would give that a probability of 0. Now, you need to know how to calculate various probabilities. And I've calculated some. I want you to be able to calculate some probabilities. And there are many sort of probability exercises that people can do. And the most important thing you should know about calculating probabilities is that it can often be done through a process of counting. Not always, but often. So probability problems can be counting problems. They aren't always, but they can be. Let me illustrate. So they can be counting problems. So in what circumstance would a probability problem really be a counting problem in disguise? Supposing you draw a card from a deck. Well, that card might be a diamond. What is the probability that the card would be a diamond? There are lots of ways to answer this, but I want to answer it by counting. And so let's count how many cards there are in a standard deck. There are 52 cards in a standard deck. So a probability that a random card is a diamond. So there are 52 cards in a standard deck. And among those 52 cards, there are 13 diamonds. And so what we do here is we take the number of successful outcomes, or the number of outcomes targeted, the number of that we're trying to calculate, and we divide by the total number of outcomes. This is very like a proportion. It's like a hypothetical proportion about all the things that could happen, and then among those things, we're just calculating, what proportion of them are the ones that are successes from this point of view. And so the probability is going to be 13 over 52. We calculate it as a proportion, which is, which is 1/4. Because these are both divisible by 13, we can just cancel this fraction, which is 0.25 or 25% if you want that as a percentage. So probability 1/4, a random card drawn is a diamond. Now this logic works so long as we are reckoning with equally likely outcomes. It's very important here that of the 52 cards, no one card is more probable or more likely to be drawn than any other. If the cards are not equally likely as draws, then this logic is not right. So this only works when we are reckoning with many equally likely outcomes and then a few that we want to find the probability of. So this works only with equally likely outcomes. And in the case of equally likely outcomes, we can calculate a probability by calculating how many things can happen, how many things are the ones we're trying to reckon with, and then divide. Let's do another example. So maybe this is example A and this is example B. So what's the probability that all four, so I'm going to introduce this problem in a minute, all four alligators are female? So supposing we have a nest of alligators and there are 4 viable eggs in that nest, I want to know the probability that all 4 of them are going to be female. And so what I'll do is I'll list all possible outcomes. Now, there are a lot of possible outcomes, right? Because if you have 4 eggs, you could sort of label them or something, 1, 2, 3, 4. And then there could be any arrangement, any assortment of female and male in those eggs. And then we want to find out what is the probability that all of them are female. So let me take a moment to write all of the possible arrangements. So this is a lengthy list of all the possible arrangements of female or male among the eggs in that nest. And it took me some time to write it out. We need to write these things out carefully. We need to make sure that we don't repeat any because then we're miscounting. We need to make sure that we don't leave any out because then we'll miscount. So this has to be done very carefully, but you can check me here. Please check me and make sure that I didn't forget any. Now, if we count them all up, there are 16 in total. How many of them are successes from the point of view of the probability that we're attempting to calculate? Only one of them, right? Only one of them has this characteristic that all 4 of the alligators in this nest are female. And so one success. Now, obviously, this thing that I'm calling a success, it's whatever probability you're trying to calculate, whatever event you're trying to get, you get an understanding of. So that's 1 in 16 is the probability. So the probability of that happening is going to be 1 in 16. So that's the answer to this problem. This problem illustrates that in order to use this counting principle, you need to have equally likely outcomes. That's very important. And you also need to be able to count them. You need to be able to count the total number of outcomes, and you need to be able to count the outcomes that are actually successes from whatever point of view you're taking. This is not always easy to do, and so so this kind of counting issues can be a problem in these things. You have to be very careful here. Now, I want to confess, just because I tried to make this example interesting, this example is interesting particularly because of how alligator sex differences happen. Alligators, as it turns out, don't actually have sex chromosomes the way most animals, including humans, do. Alligator genders are strongly influenced by the temperature of the eggs in the nest. One egg can hatch into a male or can hatch into a female depending on the temperature at a critical developmental stage of the animal. And so that actually means that this example is a little bit of a lie if you think very carefully and scientifically about how alligator genders work. And what makes it a lie is that some of these are less likely than others. Ending up with all females is actually quite likely, and ending up with all males is quite likely because maybe the nest was warm or cold during that critical phase. Ending up with an even mix of males and females is less likely. And so if you really, I mean, so this is a confession here, if you really take into account how alligator genders work, then what you see is these 16 outcomes are not all equally likely. Some of them are more likely and some of like this one, and some of them are less likely because the genders are not independent between this egg and that egg and that egg. They're determined by the environment, by the temperature of the environment. And so they tend to all roll one way or all roll the other way. And so this example is if we take that into account, this example is a bit of a lie. So forgive me. Now, the next example that I want to do is an example in which we roll dice. So imagine two six-sided dice, we roll them, and then, as is very common in mini games, after rolling the dice, we total them, right? So if one die lands on a 2 and the other die lands on a 3, then we total them and we get 5, right? So this is a very common act in many dice games. We roll 2 dice and we add the outcomes. Now, it can't be less than 2 because the smallest number on each die is going to be a 1. So 1 and 1, sometimes called snake eyes, is the smallest possible result. And it can't be more than 12 because the dice go up to 6. So 6 plus 6 is 12. That's the largest possible result. So what I want to do here is try to figure out what is the probability if we roll 2 dice of having a total on those dice, which is equal to 9. So let's do this example next. And what we'll see is there's actually some trickiness here. And there's a wrong way and a right way to think about this problem. So the probability of total 9 on 2 dice. So let me just preface this the wrong way. So the wrong way, thinking about the outcomes that are possible, is to list the total possible outcomes. Here they are. One of them is a 9. How many outcomes are there? There are 11 numbers here. It's 2 through 12. So it's the 12 numbers 1 through 12 with 1 excluded, namely 1. So that's 11 numbers. So there are 11 numbers here. One of them is the desired outcome, 1 over 11. And this is wrong. This is not the right approach to this problem. The reason this is not the right approach to this problem is that these outcomes are not equally likely. It's a lot harder to roll a 2, snake eyes, than it is to roll a 7 if you're rolling 2 dice. Because there are many ways the dice could fall and total 7, and there's only one way the dice could fall and total 2. And so this is not an appropriate calculation of the probability of getting 9 on 2 dice, and it's not the right number. What can we do instead? We need to think about what are equally likely outcomes. And so let's make a list of the outcomes that are truly equally likely. So here's the list. So here's a list of outcomes, and every pair here is supposed to represent an outcome. The first die, like this one, for example, says the first die rolls a 2, but the second die rolls a 4. This one means both dice roll 5. This one means the first die rolls a 6, but the second die rolls a 3. And each one of these represents an outcome. And I better change my title here because this is going to be the right way. Now, these outcomes, how many are there here? There are 1, 2, 3, 4, 5, 6 columns in this grid, and 1, 2, 3, 4, 5, 6 rows in this grid. And so there are 36 possible outcomes here. And these 36 possible outcomes are all equally likely, right? It's just as likely to get a 2 and a 5 as it is to get a 4 and a 2, as it is to get a 5 and a 5, as it is to get a 6 and a 5. Each one of these outcomes has a probability which is the same as all of the others. Now, so there are 36 outcomes total, and they're all equally likely, which makes this the right way. How many of these are successes from the point of view of the event that we're trying to analyze? Well, we need to figure out how many of these total 9. And so that's this one, this one, this one, and this one. Those 4 total 9. And so we have 4, we could say, successes. And so 4 over 36 is 1 over 9, which is 0.11, which is, well, or 11%. So that is the probability of rolling a 9 in the total of 2 dice. It's actually 1 in 9. It's coincidence that it's the same number there, 9. Or about 11%, which is different than the answer that we got the first time when we did it the wrong way. So this is how we can use counting principles in order to establish what is the probability of an event.